So today my talk is about these small particles. We will see which are in the, sort of a big science for the Dune project. So let me start saying that when I meet people which are not an expert, and I say that I'm part of the Dune collaboration. They are surprised, and they probably I don't think they think I'm an actor, but probably they 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 are thinking about the Dune book and movie saga. But in order to avoid any possible misunderstanding, today we will not talk about this, but this Dune, which is an acronym that stands for Deep Underground Neutrino Experiments, and this is our logo. So you can see a dune here, and also the neutrinos, which are the so-called small particle of the title of the presentation. Uh, Dune, this name is a declaration of intent. Indeed, deep underground stands for really deep underground. We will place our far detector beneath the surface at a kilometer underground, so very deep. And neutrino experiments, of course, stands for the target of our project, which is the study of neutrino, especially for let's say neutrino oscillation physics. So this is a summary of what we will see today in this presentation. I will start with a brief introduction related to the neutrinos, their history, very few slides, and basically the open questions that can be, let's say, try to solve with neutrino physics. And then I will concentrate on Dune experiment, of course, trying to give a complete overview of all the activity we are doing, so related to neutrino beam, the near detector complex, the far detector, the Cactus facility, which is the setup and apparatus that we have here in Ferrara, related to Dune, but also the prototype of Dune, which are currently taking data at CERN. And finally, if I have some time, I will compare, let's say, the sensitivity and what we will see with other experiment related to neutrino from accelerator, which are NOVA, T2K, and finally, in the end, Hypercamiocan, which is a proposed experiment for future. So, okay, neutrinos are, of course, particle described in the standard model. The electrons here in green, these three particles here. There are three families related to associated to the charged electron. So we have the electron neutrino, the mu neutrino, and the tau neutrinos. And let's say they are the most abundant particle except for in the universe, except for photons. And the important thing I would underline is that they only feel and they only interact with the weak force. So which is, let's say, many orders of magnitude less than the other forces, such as the strong or the electromagnetic force. So it's let's say an experiment issue. In fact, as we will see, in order to be able to detect neutrinos, we should build large experiments, so with large volume. And okay, there are many sources of neutrinos. Let's say neutrino from the sun, atmospheric neutrinos, nuclear beta decay, the power plant, but also accelerators, which are the let's say main topic of this talk. Also, humans are sources of neutrino, and this is the number. So we emit 3 billion neutrinos per day. So it's a large quantity, let's say. So this is the historical point of view. So neutrino were proposed by Pauli in let's say 100 years ago to ensure the energy conservation in the nuclear beta decay, and he let's say he bet that nobody were able in future to discover neutrinos, but unfortunately for him, in the 50s, two guys, Raines and Cohen, discovered neutrinos with a detector, which is this one, placed nearby a nuclear power plant, and exploiting the so-called inverse beta decay. Sorry if the figure is not well enough here. And they were able to identify few neutrinos per hour. So at the end of the experiment, they obtain a lot of signals in order to do some good statistics. And why neutrinos are so it's so hard to measure a neutrino signal? Because as I said previously, they only feel the weak force. So basically, there are two types of interaction that they can feel depending on the boson. So with the Z0, they can interact with the neutral current, or otherwise, if the boson is ZW, we have a charge current, and as you can see here, the electron neutrinos are associated with the electron, the muon neutrino with the muon, or tau, the neutrino tau with the tau. This is a plot of the cross-section, the total cross-section here of neutrino, and as you can see, this number is, let's say, order of magnitude less than, for example, the one of proton in argon or other. So this is the reason why it's experimentally difficult to probe neutrinos, basically. So an interesting properties of neutrino, which is something that we will measure in Dune, is the neutrino oscillation. As I said, neutrino exists in three flavor states, which are electron, neutrino, muon, tau, but also we can write them in terms of their masses, so neutrino 1, neutrino 2, and neutrino 3. And the matrix here is the so-called Pontecorvo-Nakagawa-Sakata matrix, so PMNS, which allow us to explain these bases in these others. So, I mean, electron neutrino, for example, in terms of Ni1, Ni2, and Ni3. And this means that if you have a neutrino here and you measure, let's say, and you know that is an electron neutrino, and you measure again after a certain distance, this neutrino can be a neutrino with another flavor. So, for example, a mu neutrino. And this is the so-called neutrino oscillation. And here is the equation that describes this behavior if we only have two flavors. So, in a simplified version of Ni alpha and Ni beta, but it's important because we can see here the important quantities that play a fundamental role, which are the angle theta, which is 1 here, but is of course 3 considering all the three states. The mass square difference, which is this term here. Also here we have three terms, and then the experimental, let's say, parameter, which is L over E, where L is the distance from the source to the final measurement point, and E is the energy of the neutrino. Then the other parameter of the matrix here is delta, which is related to the CP violation symmetry. In fact, if we have a neutrino or antineutrino, they behave different, and if delta is 0, this means we do not have symmetry violation. Otherwise, CP is violated, so it's an extremely important parameter to be measured. So, neutrinos are extremely important to be studied because there are a lot of open questions related, of course, to neutrinos, such as we don't know the absolute masses of this particle. Also, the mass hierarchy, or better, if is Ni1, Ni2, Ni3, or Ni2, 3, and then Ni1. So the ordering problem. We don't know if they are Dirac or Majorana particles, of course, and also, let's say, in the standard model we have only three flavor states, but there are some theories that foresee more states, the so-called sterile neutrinos. So also in this case, there are many studies to be done. Also related to this question related to neutrinos, we have more general questions. The one related to CP violation, as I said previously, but also to the fundamental symmetries of the universe, or if some grand unified theory exists. So, let's say, the point here is that it is important to study neutrinos, and there are many ways to do this. Of course, one is studying atmospheric neutrinos, but also neutrinos from the sun, from a nuclear reactor, or produced by accelerator. And today we concentrate on this last one. So we will see how can we do this and try to solve this question with Dune. So Dune is a long baseline neutrino experiment. Long baseline means that the distance from the source here to the far detector is long, is 1,300 kilometers. We produce our neutrinos at Fermilab in Chicago, and we will measure them in South Dakota in an underground mine at a kilometer underground. And we have two sets of detector, two complexes. One is placed here at a few hundred meters from the source, and the other, as I said, is at the end of this baseline. Dune will exploit a broadband neutrino beam, so neutrinos will have energy from 0.5 to 4 GeV and high intensity flux, higher than 2 megawatt at the phase 2 of the project. And we will exploit the liquid argon type projection chamber technology for our detectors. We will see later in the next slide how it works. Also, another important pillar is that the near detectors should move both on axis and off axis in order to probe different angles in the neutrino beam, and these are the goals that we would like to announce in our physics program. So basically, the SIP violation, the mass hierarchy of the neutrinos, a precise measurement of the oscillation parameters, but also study on proton decay, on neutrino from supernova, or other study of the so-called physics beyond standard model. So let's start with the production of neutrino. So neutrino, as I said, will be produced at Fermilab using the main injection from protons that will at the beginning of the project operate at 1.2 megawatt and then upgraded to 2.4 megawatt with the so-called proton improvement plan. And we will, let's say, our beam, proton beam will be tunable in this range from 60 to 120 GeV. These are some images of the RF cavity for accelerator, the Fermilab complex. But how we can produce a neutrino? Of course, neutrinos are neutral particles, so we cannot accelerate directly them. So the first step is to accelerate the protons on a graphite target. Then there are there's the production of secondary particles, especially pions and kaons, and we will exploit the pions decay, which let's say, which ends in muons and anti-muons and anti-neutrino or neutrino, depending on the charge of the pions. So selecting positive or negative pions, we can select one decay channel, and so at the end we will have a neutrino or an anti-neutrino beam. And this is exactly what we will do in Dune. Then once we have our neutrino beam, we should measure precisely the feature of this beam, so the flux, the composition, and we will do this exploiting the near detector complex, which is composed of 3 submodules. We have a near detector liquid argon time projection chamber, which is this one here, coupled with a muon spectrometer, which is shown here. These 2 detectors, as I said, can move in this direction, so orthogonally to the beam, and probe different angles. Instead, at the end, we have send, which is this one, and is fixed on axis. So with all this stuff here, we will be able to, let's say, precisely measure neutrino composition, neutrino flux, and also precisely the neutrino to argon cross section, which is important because the argon is the target material also for the FAD detector. In the near detector, we expect to have 50 neutrinos per bunch, so in total 10 to the 7 neutrinos per year. So let's say a large number to do a good statistic. And here you can see the, as I said, moving of axis. One can select precisely the energy of the neutrino. So on axis, as June is, we have a broadband spectrum, this one. Instead, as other experiment we will see later, for example, T2K, like they exploit off-axis beam, so maintaining the detector at a given angle, they have a narrow beam, as you can see there. So, NDLR and TMS form this prism, which is the movable detector. NDLR, as the name suggests, is composed of liquid argon time projection chambers, many modules. So we have a high granularity detector because of the, let's say, pile up of neutrinos in this near detector. The module are this one, which are 1 by 1 by 3 meters long, and there are currently some prototype at Fermilab, which are working. And coupled to it, we have the TMS, which is the muospectrometer, which is in the actual design similar to Minos, but in future will be upgraded to a more sophisticated detector to measure precisely some quantities. So now it's just a planes of scintillators and still here to measure basically the muons that escapes from the NDLR. And later on we have, as I said previously, SEND, which is a refurbished detector. SEND is now through experiment at Frascati, and now we're refurbishing in terms of the inner tracker, the calorimeter, and some part of the magnet. And let's say these are the main goal of this subdetector. So give an independent measure of the flux and then the energy of the neutrinos, the neutrino beam, and constrain systematic from nuclear effect. And also, since in the inner part we have this small vessel here, which is called grain, which is a liquid argon imaging camera, we can, let's say, use two different target material to reduce systematics or strange effect. So it's an important part of the detector. And the tracker here, let's say, the baseline detector is a stroke tube tracker. So let's now move to the FAD detectors. The far detectors, as I said, are placed in SURF laboratory in South Dakota, and they are very large time projection chamber with the dimensions of 20 by 20 by 70 meters. So you have to imagine two G building, one on top of the other, and these are the dimensions. And this is the picture of the cavern, which was excavated during last year. So the caverns are ready to host this very large cryostats, which contains each 17 kilotons of liquid argon. So very large amount of argon. And as you can see here, we foresee to have 4 modules. For the phase 1, only 2, these 2 one here, 1 and 2. And in the future also the other. These 2 modules will exploit 2 different technology, as we will see in the next slide. The important part here is that with the far detector we should be able to identify precisely different flavors of neutrinos and precisely reconstruct also the neutrino energy. So, as I said, they are liquid argon time projection chambers, but what is a time projection chamber? So basically, is a chamber in which you can reconstruct the tracks of the charged particle produced after the neutrino interaction here and the energy. And it is made something like this, in which you have an electric field here. So when the charged particle here releases its energy, it ionizes the argon atoms. So we have charge produced that can drift and reach the anode, which in this case is different planes of wires that can be also pixelated anode, and you can reconstruct the tracks and the energy here. And to measure the timestamp of the events, you can exploit the scintillation of argon, which is a prompt signal. So then you can reconstruct this the Z dimension. In the far detector, we will have 1,000 events of neutrino per year. So order of magnitude less than at the near detector, but sufficient to do a good study of neutrino oscillation. These are some argon properties related to the ionization or the scintillation like it. Far detector module 1 and 2 will exploit 2 different technologies, the horizontal and the vertical drift. The horizontal, as the name suggests, we have the electric field, which is directed horizontally. In total, we have 4 drift regions, so 2 cathodes playing here and 3 anodes, which are instrumented with 3 planes of wires, as in the previous in the slide of the previous in the image of the previous slide. And the maximum drift here is 3.5 meters with an electric field of 500 volts centimeter. In the vertical drift, instead the electric field is directed vertically. We have only one cathode, central cathode here, and through two drift region on the top and on the bottom part with a pixelated charge without planes, this one here, and this white squares here are the photo detector modules, so uh, to give the timestamp of the event, basically. As I said, here and here we have many meters of drift length, and so the let's say the purity of the argon is extremely important. Otherwise, electrons will be captured by high electronegativity impurities, and they cannot drift toward the anode. And given the drift velocity, the requirement in terms of distance is 10 milliseconds for the vertical drift, for the let's say the electron drift lifetime. And this is important because this means that the oxygen equivalent concentration must be lower than 30 ppt, so 30 part per trillion. And if you do this simple calculation, this means that you need less than a needle in the G building of impurities. So it's a very small amount of purity that we can tolerate within the far detector. And so how can we obtain argon and argon with this purity? Basically, argon you can buy from companies. Argon is so-called rare gas, but is not so rare. In fact, it is 1% of the air. And so companies liquefy the air and then distillate with a similar process. For example, of that one used for the distillation of grapes. As well. And then, in order to reach the very high purity of 30 ppt, we have to filter with this stuff here, which are fine metal silver, alumina with copper spheres, and flowing the argon through this filter, we can purify at a level of 30 part per trillion, which is what we need. And instead, related to the light, since as I said, we have this very large cryostat of 20 by 20 by 60 meters. So we cannot instrument all the chamber with light sensors. And so colleagues from Brazil developed these devices, which are called X-Arapuca. Arapuca is the stuff here, is the trap for birds that they use in Brazil, in Amazonia region. And this Arapuca acts as a light trap. So the under 28 nanometer light from scintillation of argon enter this wavelength shifter bars and is converted into 350 nanometers. Then we have a dichroic filter here. So this light can pass and reach this other wavelength shifter that converts again to 430 nanometer, but these photons cannot escape because of the dichroic filter, so they are reflected, and after many reflections, they finally can reach a silicon photomultiplier, which is the core of our photodetector modules. In total, we have in the far detector horizontal drift 300 300,000 sensors with an area of 6 by 6, which are these ones shown here, mounted in this board of 6 photo detectors. And of course, we need to test them before the installation to be sure that their features are exactly what the expected ones. And so we developed this setup, which is called Cactus, which is here in Ferrari, in the laboratory, which allow to test 120 CPM per run of measurement. And so in total, we are testing all the 300,000 sensors with this setup, and the other 4 that are placed in Bologna, Milano, Granada, and Prague. So I would like to thank especially the INFM section here, which gave us very, let's say, an important contribution to the development, especially for the electronic part. And these are some results for fun related to the main parameters of these silicon PM sensors, so the distribution, the background voltage, the quench resistor, the dark count rate, and let's say this is before and after thermal cycles in order to test the thermal resilience of the sensors. But okay, let's go back to Dune and see something about the prototypes of Dune. As I said at the beginning, at CERN there are 2 prototypes, which are called ProtoDune, and starting from 2018, they are used to test and to verify the technology that will be used in Dune. So at the beginning, they were instrumented with photomultiplier tube, then with silicon photomultiplier. Then we are now testing the horizontal drift and vertical drift technology. So we would like to test in a large scale prototype, since they are 7 by 7 by 7 meter cryostats, the final technology to be sure it will work for Dune. And not only the technology, but also the algorithm and the electronic part. But also we are doing some physics related to, for example, the cross-section measurements of particles in argon, or the measurement of the cosmic muon flux and other. These are preliminary results that are that will be published soon, I hope. So let's see something about the sensitivity, the expected sensitivity of Dune related to the 2 more interesting quantities we would like to measure, which are the delta CP, so the third-party violation phase, and the mass ordering of neutrinos. As you can see here from this plot, this one on the top are for the neutrino mode, and on the bottom for the anti-neutrino mode. So you can see that let's say a measure of an increase of electron with respect to entire neutrino, electron neutrino, or a reduction is a measure of these parameters. And so we expect to give an hint on both these 2 quantities in the, let's say, the last few years, in the first year of measurements. In particular, for the best case scenario, we expect to have a 5 sigma sensitivity in 1 year here. This is the best case scenario where the violation phase is maximal here. Instead, in the worst case, we should test all the possible values. So in that case, of course, the time increases. So in the worst case, we can give an answer to the mass ordering at 5 sigma in 3 years, let's say. Instead, related to the charge parity violation sensitivity, also here, in the best case, in 3 years, we will be able to have a sensitivity at 3 sigma. Otherwise, on the long term, we should test all the possible value of this phase, and so in order to have a 3 sigma sensitivity of the charge parity violation, we need, let's say, more than 10 years, 12, 15 years. And this is the expected resolution of the angle. So, okay, not only delta CP and mass ordering, but also we will be we will measure neutrino from supernova. No, it does not depend on us, but on supernova. But let's hope with a good pointing resolution, as you can see here, and also from this we can give an hint on the mass hierarchy, since the time let's say behavior of the burst, the neutrino burst, is different depending on the hierarchy of the neutrinos. Also, we would like to measure neutrino from the sun and possibility to sterile neutrino. This is an example of the probability of oscillation, considering not only 3 neutrinos, but one more, so one sterile, and you can see that in that case we will see very different behavior. So this is an indirect test, but also some very standard model physics, such as dark matter or very weakly interactive particles, just this one. The status. Currently, neutrino beam, let's say the RF cavity are ready and arrived at Fermi National Laboratories. They are building a new building here for the cooling unit. So in a few years, hopefully this will be related to the near detectors. The final review is ongoing. Related to the liquid argon prototype for NDLR, there is a prototype, of course, in operation, Fermi Lab, and the construction of few modules will start very soon. And related to send the detector, so Chloe is infrascati, is still infrascati, and it is there are a lot of work for the so-called Chloe to send project. So they are dismounting the calorimeter and refurbishing the electronic, the photo detectors, and so on. And later on, the detector will be shipped to Fermilab. At SURF, as I said, the caverns are ready. and the two cryostats, so horizontal drift and vertical drift, arrived in the surface laboratory. Basically, one unfortunately with two accidents. Hopefully, nothing too bad happened, but we will see when we will mount in the cabin. And this, let's say, the beginning of building the two cryostats will start at the probably in 2026, so the next year. Related to Protodune, in this winter, there was an accident. Unfortunately, nobody died, so it's okay. But there was a complication in the rules. So finally, we have now the access again to the neutrino platform area, and so we are ready to restart the measurement with Protodune. And also the analysis of the past data of the last years are ongoing. Apart from the scientific questions, also the funding situation in the US is not clear at all. So this is let's say, something that we have to take into account, especially for the phase 2 of the project. For the, let's say, long-term part of it. And for the future, we will start our phase 1 in basically 2030, so in 5 years from now, 6 years from now, with two far detector liquid ion type injection chambers modules, horizontal and vertical drift, with a complete near detector with the liquid argon and TMS, so the muon spectrometer, and send, and with the standard beam at 1.2 megawatts. The additional phase 2 instead will use an upgraded beam and two more far detector modules, but will start in 2035, 2036, so few years later. So this is more or less what I would like to say about Dune, and if I have few minutes more, I can say something about the, let's say, the competitors of Dune in terms of experiment that uses accelerator. So these three here, the SBNL at Seminario M, T2K, and for future at Lacuna. Of course, there are many other experiments on neutrino. So, for example, I know that here in Ferrara there are a group involved in Juno, previously in Borexino, but I will concentrate only on neutrino from accelerator. So the short baseline is short baseline, of course. At Fermilab, we have also here three detectors. The SB1D placed nearby the source at Fermilab, 100 meters distant from the target. An intermediate, which is Microboon, a few hundred meters distant, and finally Icarus, which is the, let's say, the Rubbia detector that was previously installed in Gran Sasso laboratory, and then at CERN, and then finally it moved to Fermilab. SBND is, let's say, has two main goals. One is to test neutrino-argon interaction, also related to the Dune project in the JAV energy range, since they are, especially SBND, since it is mount installed very close to the source, they will handle a large quantity of neutrinos per year, so they will study very well neutrino-argon interaction, and also they will verify some oscillation anomalies that were found by mini-boom previously, but seems not was a problem of that kind of detect. Remaining at Fermilab, we have also NOVA, which is a long baseline. So from Fermilab to Schieber in Minnesota, which is an experiment that do not exploit the liquid argon, but liquid scintillator. Both the near and the far detector are these modules filled with liquid scintillator and optical fibers, with a high granularity to reconstruct more or less everything, especially because they are placed in the surface, so they are affected by a lot of cosmics, as you can see here. And these are some preliminary results that are related to the mass ordering. As you can see, this is the latest one. They handle with a small quantity of neutrinos from Fermilab, so of the order of a few, let's say, few tenths. Here the maximum is 60, so not too much. Instead, moving to the other large experiment that exploit neutrino from accelerator. So in Japan, we have T2K, which stands for Tokai to Kamioka. Tokai is the place where neutrino are produced in the J-Park accelerator, and Kamioka is the far detector mine. More or less 300 kilometers distant. Differently from Dune, they are a no-faxel experiment at 2.5 degrees, so they have a narrow energy beam of neutrinos centered at 600 MeV, and this is because they cannot reconstruct the energy of the interactive neutrino because they exploit the Cherenkov effect in a large water tank, such as this one. This is the Super K, Super Kamiokan detector, which is the far detector, and this is a very large vessel of few meter high diameter, containing which contains 50 kilotons of water, a kilometer underground. And also they have this near detector placed near the neutrino source. They measure precisely neutrino flux and composition at the beginning, and in the far detector, these are the almost real-time event. You can go to their webpage and download the real-time events. So this is a real event of a few minutes ago, a few hours ago. And this is the two shapes of Cherenkov rings that they see for electron-neutrino light and muon light neutrinos. So they are able to distinguish between the two, looking at the shape of the Cherenkov cone. The important thing of T2K is that in 2020 they gave the first hint of CP evaluation phase in the neutrino sector. So basically they observed 90 electron neutrino and 50 electron antineutrino, and these are the expectations in the case of delta CP minus 90 or plus 90, and let's say with a more sophisticated analysis than this, they disfavored at 3 sigma the values of delta CP in the range 0 to pi. They are now running a second phase experiment with some upgrade, and they would like to measure more precisely some oscillation parameters and also confirm or not confirm at more precision level than 3 sigma this number here. And finally, let's say an upgrade of T2K will be hyper-Kamiokande, which will exploit a larger detector here, again in Kamioka mine, but a few kilometers far from Super K, which will be a 260 kiloton water tank, so 50 meter high and 74 meter diameter. This is the excavation of the cavern during the spring, and they will start operation in 2030. So this will be a direct competitor of Dune. So also they will measure at a few sigma coordinates level the value of delta CP and mass ordering, and also the other, let's say, neutrino parameters, the possible supernova core collapse or solar and geoneutrinos. So, okay. In conclusion, Dune is a long design neutrino oscillation experiment in the United States that exploit a complex of detector near the source at FNAL, and a group of detectors a kilometer underground, 1,300 kilometers far from the neutrino source. There are different prototypes of CERN to test and validate this technology. We foresee to start the data taking in the early 2030s, and given the let's say the feature of this experiment, which is the long distance, so large matter effect, the broad energy spectrum, and the high intensity beam, we would like to give a definitive answer in the quest for charge parity violation, neutrino mass ordering, and the other parameters of neutrino oscillation in the next 2 decades, let's say. So this is